So today we're going to be learning about section 4.5, which is on global wind patterns. Now the learning objective for today is that you can explain how environmental factors can result in atmospheric circulation. And we're going to learn how 3 different factors impact atmospheric circulation. We're going to learn about energy from sunlight, density properties of air, and the rotation of Earth, also known as the Coriolis Effect. So you're going to learn about all these things and how these all have an impact on atmospheric circulation of wind patterns. So we're going to start out with some basic properties about air. Now, the first thing that you need to know is that warm air expands and it rises. So if you think about a house that has an attic in the summertime, that attic is going to get really hot because the warm air is going to rise up. So it'll be hotter in the attic than it is on the lower level. Now, warm air is able to hold more moisture than cold air is able to. So if you think of the fact during the winter, how your hands get all kind of dry and cracked and your skin gets dry, that is because during the summer, warm air is actually going to have more moisture in it. So the cold winter air is actually going to be drier. There's going to be less moisture in it, which is why your skin then loses that moisture and feels dry. Now, cold air cannot hold on to as much water vapor, which is why cold air is going to be less moisturizing. But what this also means is that as air gets colder, it's going to condense, which is going to cause rain droplets to form. Additionally, another factor is that as we have this warm air rising, eventually it's going to start cooling down. Think about the fact that if you go up on a mountain up high, it's much colder than down here at sea level. So as you have this warm air rising, it's slowly going to start cooling as it moves up. And eventually it's going to get to a point where it gets cold enough that it's condensing, it's more dense, the particles are closer together, which is going to cause it to sink down. Now, because of these properties, this results in something called convection, which is basically just the circular movement of air due to these heating and cooling properties. But I'm going to walk you through this diagram to kind of talk about the importance of these properties and how it leads to cycling of air. So first of all, this is us if we were to look straight on at the surface of the Earth. So this is going to be the surface. Up on top here is going to be more in the atmosphere. And right here in the middle, we've got the equator. Now, the equator is going to be the area where we get more direct sunlight, and it's going to be warmer. So as this air warms, it's going to start rising, which we start seeing at phase 1. Now, phase 2, remember, as it starts rising up, it does get cooler as you go up. So the air is going to start cooling a bit. And colder air cannot hold onto as much water vapor. So eventually, as you're moving up, you're going to hit this point called the dew point, where essentially the air cannot hold onto its water vapor anymore. And this is going to cause condensation, and it's going to cause rain, which is why you tend to see clouds kind of all at the same level. It's because they're all hitting this dew point at the same point, and they're going to start dropping that rain. Now, the air is going to keep moving up, but it is still going to keep cooling as it's rising higher and higher. So at stage 3, we're seeing it continuing to cool, even though it's still rising at this point. But by point 4, we see it has cooled enough that it is now condensing. Those particles are getting closer, and it's going to start sinking. Now, phase 5 shows us that this cool, dry air, it's going to sink back down to Earth at the 30-degree latitude, north and south. This is just due to the fact of how long it takes for it to cool, and then when it starts dropping off, this is just where we see it, is at 30 degrees north and south. Now, what we end up seeing in these areas is that deserts form, because remember that this water was turned into rain, all the water vapor at this area. So by the time we get here, this is really dry air, and as it comes down, it's going to come and it's going to form deserts. As it gets warmer as it comes down, it'll end up being warm air that hits this point, but it's dry. And that's why we get deserts in this area. Now, there's another important thing to be aware of as we see this cycling and movement is it creates different pressures in different areas. So at the 30-degree mark, where we have all this air coming and pushing down, that means there's going to be higher pressure here. And then in the area of the equator, this is going to be much lower pressure because we have the air moving up. So in addition to this hot-cold cycling, we're also going to have this pressure is going to continue to have the air is going to be lifted up in low pressure. It's going to come down in high pressure, and it's going to keep kind of moving that cycle so that the air that's coming down at the high pressure is then going to get cycled, and it's going to continue this cycling over and over. So because of these properties, we end up getting 3 different types of atmospheric circulation cells, these areas where the air is circulating in a certain way. Now, the first one is called a Hadley cell, and that's what I just described in the last slides. This is where we get warm air rising at the equator, it cools, and it drops down at the 30-degree latitudes. The next one that's also based on temperature is going to be at polar cells. And those are named polar because they happen at the poles. So if you think about the temperature at the poles, at the very edge of the pole, or the very center of the pole, this is where it's going to be really cold. And so remember, cold air is going to condense and drop. So we start seeing this cold air dropping right at the poles. Now, as it moves, because of that pressure differential, it's going to be moving south. As you move down in latitude, you're slowly getting closer to the equator, which means it's getting warmer as you move down. So this air is going to start out cool in the middle. It's going to start moving down. It's going to start warming up a bit, which means it's going to rise again. And then after it rises, it goes through that cooling, it comes down at the pole, and it keeps cycling. Now, the third type that we have is this feral cell. And the feral cell is basically, it's just kind of this middle cell. It is going to move in the opposite direction of the Hadley and the polar cells. And it sort of acts like a gear. If you think of how gears turn and kind of push each other, that's what this feral cell is going to do for the other 2 types of cell. It's going to act kind of like this gear in between. And so all 3 of these are going to keep cycling in the same way with those same pressures at the latitudes. Now, these patterns actually are going to cause Earth's climate. So in areas where air is rising, you're going to have a lot of water condensing as it moves up that rising point, and it's going to start raining. So these are going to be areas where you get a lot of rainfall. Think of here at the equator where you get tropical rainforests. They get a lot of rain. That's because this is an area where air is rising because there's low pressure. Now, also think about the areas where air is going to be sinking. As I just talked about, this air is not going to have water vapor in it. It's going to be really dry. So this is going to lead to deserts. If you think here along the 30-degree latitude is going to be about North Africa, and we have deserts there. That's because this is an area where we have dry air coming down from these cells. So we've talked about how temperature and how density properties are going to impact the movement of air. Now there's another thing called the Coriolis Effect, and this is going to be because of how Earth rotates. Now the Coriolis Effect is going to be the deflection of objects traveling through the atmosphere due to the spin of Earth. So keep in mind that Earth is going to spin from west to east. It's going counterclockwise, and it's moving really fast. However, it's going to move at different speeds at different latitudes. So think of the fact that Earth has to make a full rotation in 24 hours. Now, if you are down at the equator, in order to make that entire circle, you got to move really fast to do it in 24 hours. So we see that at these latitudes, the speed is actually at about 1,600 kilometers an hour. But if you go up towards the pole, they're right there at that center point. In order to go around in the circle, it's really little. So it actually almost barely has to move in order to rotate in 24 hours because it's a really tiny circle there. So we see at different latitudes, there's going to be different speeds that the Earth is moving. Now, this matters for this thing called the Coriolis Effect. Now, This is kind of a confusing topic, so I'm going to try to explain it in a few different ways, but I realize it's a bit of a doozy. So what we are going to see is the direction of rotation as it's spinning. When things are moving on the surface, we are going to see a different way that it moves based on whether it's going from areas of low speed to high speed or from areas of high speed to low speed. So the way I'm going to explain this is think about it kind of like a treadmill. If you were here in the middle moving on a treadmill that was going like 15 miles an hour and you were running on it. Now right next to it is a treadmill going 2 miles an hour. If you were running on that 15 mile an hour treadmill and all of a sudden you hopped over to that 2 mile an hour treadmill, you're going to be running fast enough that you're actually going to like overshoot and go past that spot that you were running at on the 15 mile an hour treadmill. And so we're going to see you actually kind of overshoot it. Now think about the opposite. If you were on a 2 mile an hour treadmill, then you are going to be running pretty slowly. If you were to go and hop to a 15 mile an hour treadmill, you would all of a sudden like get really behind because you're moving too slow for this really fast moving and you would be at a different point. This is kind of how it works with something that is moving along the rotation of Earth. And so if you were to be in the middle here, and let's say that we have wind coming down in this area, like at the 30-degree latitude, and it's moving towards the 800 or towards the 60-degree latitude, it's going to go from an area of moving fast to an area of moving slow. And so it's going to kind of overshoot that amount. And if you were coming from an area where you were moving slow and the Earth is rotating really fast, by the time you hit here, you would be moving not fast enough so that you would be behind. Now, the Coriolis effect is based on kind of perception. So I'm going to explain it in a different way too. I'm going to give you a lot of examples and maybe one of them will stick. So imagine that you were standing at the North Pole and you were going to throw a baseball. If you were to throw that baseball straight, pretend the Earth isn't moving at all. This dotted line here is going to be the path that the ball would follow. It would just go straight. However, in reality, Earth is moving. So even though you threw that ball straight, the Earth is going to move underneath it. So it's going to seem like this ball ended up at a different spot. It got deflected because the ball kept moving straight, but the Earth moved under it. So it landed at a spot that would be behind where it would have originally gone. And that's the Coriolis effect. The Coriolis effect is the idea of when you're moving, with the Earth is moving, it's going to cause this deflection in things that are moving above it. What we are talking about is air moving above it. So essentially, this diagram on the right here, what we are seeing is that objects moving from the equator towards the poles are going to moving in a region of slower rotational speed, and they're coming from a higher rotational speed. So their paths are going to be deflected ahead of the point of origin. Now, these green ones, if we're moving from areas of high latitudes to low latitudes, you're going from a region of low speed to a region of higher rotation speed. So therefore, there's a deflection behind the point of origin. Now, if you look at the southern hemisphere, it's going to follow this same principle, but it will move the opposite way. Just again, picture you're like throwing that baseball. If you're throwing the baseball this way, it's going to go one direction. If you throw it this way, it's going to go the other direction based on the speed and based on your original way that you were looking. So here's what this means for the wind. This is kind of all the background behind to explain how wind moves. Wind is going to move between the 0 to 30 degree. It's going to move from east to west. As you're seeing, from the 0 to the 30, it moves from east to west. From east to west. Now, this is because the Earth is spinning faster at 0 degrees than at 30 degrees. And the wind is going to get behind as it moves from a slow to a fast area. Now, wind between the 30 to the 60 degree is going to move west to east. And this is because Earth is going to be spinning slower at 60 degrees than 30 degrees. So the wind's going to get ahead. It'd be like jumping from that 15 mile an hour to the 2 mile an hour treadmill. And it's going to get ahead as it moves from a fast to a slow area. So that's the Coriolis effect. Now here's where we bring it all together. This is going to be affecting our global wind patterns. So not only do we have all this cycling of the different cells, we also have the Coriolis effect going on. So you're getting all these little mini cycles of moving from high to low latitudes or from low to high latitudes based on the cells. Hadley cells, remember, they go up at the 0, they come down at the 30. So they'll be moving from high to low latitudes. Barrel cells come down at the 30. They push up towards the 60. So they will be going from low to high latitudes, which is why we see all these different shifting based on the Coriolis effect. So here's what this means for wind patterns. All these things come together and they determined how wind moves in our planet. So air is going to move out from the 30 degree to the 0 and the 60 degrees due to these high pressures and low pressures. So again, just think of each of the cells. It's going to be coming down at the high, up at the low. And we're seeing that in each of these areas. And then what this is going to cause is the 0 to 30 winds blow from east to west. These are called the eastern trade winds. And these are going to drive ocean currents clockwise in the north hemisphere and counterclockwise in the southern hemisphere. This is because up here in the north hemisphere, remember the way that we're moving, because we are moving from 30 to 0, it's going to push it in this way, and we're going to see this swooping down, and it will be moving clockwise. Now, if we're coming from down to up, the southern hemisphere, we've still got this Hadley cell, so we're moving from 30 to 0. It's just going to give us a counter clockwise in the southern hemisphere. And this is why hurricanes in the northern hemisphere move clockwise, and hurricanes in the southern hemisphere are going to move the opposite way. Now, up in the 30 to 60 degree latitudes, this is where the winds are going to blow from west to east. They're known as the westerlies. That's what the winds are called. And these are going to drive weather patterns of North America. So think about in North America, you're going to be having weather moving from west east because that's the direction that the winds are moving. So this is how we get all three of those factors moving together to explain why we have these patterns in global wind. So your practice FRQ for 4.5, I want you to look at this diagram here. You're going to explain how the sun is responsible for the pattern of air circulation that's seen in cycle C, right here, from the 0 to 30 degree latitude. So in cycle C, explain how the sun is responsible for this pattern. So that's going to be your practice FRQ for 4.5, and those were your notes on 4.5.